Welcome to Sovereign Health August webinar on Addiction and the Brain by Dr. Dan Arnault. Sovereign Health Group specializes in treating individuals suffering from addiction, mental health disorders, or dual diagnosis. We customize each treatment plan to the patient using proven biopsychosocial treatment modalities for a well-balanced and holistic approach. Our innovative programs include state-of-the-art therapeutic methods that address all underlying and co-occurring conditions to reduce the risks of relapse. Today, presenting on addiction in the brain, we have Dr. Dan Arnault. Dr. Dan Arnault has been working in the field of addiction for 6 years. He graduated from UC Berkeley with a bachelor's in biology and then obtained his medical degree from Texas Tech Medical School and did his residency at the University of Oklahoma Health Sciences Center. He is board certified with the American Board of Addiction Medicine and is currently the medical director at Sovereign Health in Culver City, California. Everyone, please welcome Dr. Dan Arnault.
All right, thank you, and welcome to everybody in the audience and anybody who may be looking at this webinar later on. I think the introduction pretty much said it all. So I'll just go ahead and go right into this. We start off just with a few things about the brain. The brain, an immensely complex organ in the body, 100 billion nerve cells or neurons. And if you hear me using those terms, those are synonymous. So we say neurons, we're talking about the nerve cells. And it has about 500 trillion connections. So that just gives you some idea of the complexity. And if we look at the next slide here, we've got a schematic of a neuron or a nerve cell, and then we've got a couple others actual neurons that are stained so that you can see them. If you look in the top left, you see the dendrites. That's where the signal is first received by the nerve, and then it travels along the long part of the nerve, the axon, and then it'll get to the end, the axon terminal, and that's where all the neurotransmitters and chemicals are released. And that's where everything big sort of takes place. Lower down on the left-hand side, you'll also see neurons, actual pictures of neurons. This one has a few connections to the next one. And then on the right-hand side, you see a Purkinje cell in the brain, and that can have as many as over 100,000 connections. So neurons can have connection. There are neurons that have connection to one other neuron, and there are others that have connections to over 100,000 different neurons. So I put this up here just to give to get a better understanding. We don't need to be neuroscientists or anything like that to understand some basic things about nerve transmission. The nerve cell on the left, as the signal is traveling along the long part of the axon of that nerve, when it gets to the end, there are vesicles which contain the neurotransmitters, and those are going to be migrate to the end of the nerve, fuse with the membrane, and release all those neurotransmitters into that little space, the synapse or synaptic gap. Then it's going to bind to the receptors that you have on the other side, and once it binds to the receptors, then the signal can then travel along the next neuron. So that's how the signal gets from one to the next. Now, the significance of that is that these different chemicals, these different neurotransmitters, have different functions, and that becomes very important to understanding addiction. They may have one function in one part of the brain or the central nervous system, have a different function in different parts. Dopamine, which is the big neurotransmitter in addiction, the one that we'll be talking about the most. In the reward pathway, it gives you that sense of euphoria, but it's also involved in movement, and there's a part of the brain called the substantia nigra in Parkinson's that has a lot of dopamine-containing cells, and those degenerate in Parkinson's disease. Okay, but we're going to focus mainly on the effect that dopamine has in the reward pathway and the euphoria. And in 1954, this is really where I think our understanding of addiction really became more of a modern science, and we took a big leap forward you had these two guys in 1954, James Olds and Peter Milner, who were doing experiments on rats, and they were not looking for anything related to addiction at all. They were looking to see if they stimulated a certain part of the rat's brain, it would influence whether it would turn to the left or to the right, and which direction it would go in a maze. They missed their target, and when they stimulated that part of the brain, they found that the rat sat up, it looked around, sniffed, and it appeared to them that it really liked this stimulation it was getting to this part of the brain. So they set up something up where the rat could actually press a lever in order to stimulate that part of its brain itself. And so what did they find? They found that the rats would press that lever up to 5,000 times in an hour. And in fact, that was the only thing they did. They wouldn't eat, they wouldn't sleep, they wouldn't drink any water, and they would actually die from starvation or dehydration as a result of that. Some other neuroscientists took that even further, and they would put a grate with an electrical current running through it. And so the rat would have to stand on that grate in order to press the lever. And so it would still continue to press the lever in the same way while this electrical current was actually being pumped through the grate and pumped through its body, and it would actually die, it would actually fry and get electrocuted to death just in order to stay on this grate and to continue to press that button. And then later researchers found that there were other areas of the brain as well where they get the same thing. Now later on, this part of the brain that was being stimulated by the rat that would make them press this lever over and over again, they called it the nucleus accumbens. And they found out that dopamine was released in large amounts when that area was stimulated. They found other areas of the brain as well where you got that same kind of thing where if you stimulated the brain, then they would, if they could stimulate it themselves, they would keep on pressing that lever 5,000 times in an hour. But they found that all of those other areas always fed directly into the nucleus accumbens and would result in that release of dopamine. So all of these areas had that in common. If it was a pleasure center, if it was something that that stimulated euphoria, and it had this reaction where the rat would continue to press the lever in the way that I just described, it was all connected always to the nucleus accumbens and the release of dopamine from that area. It's also sometimes called the anterior striatum. You're probably going to see nucleus accumbens more, but just in case you come upon that term, if you see anterior striatum, they're talking about the nucleus accumbens as well. So here we see, we can see where this is, and I'm going to try to see if maybe sometime in the future I can get a webinar where I can use some of my software on my iPad to show you, you can manipulate the anatomy and the brain and take things away and put them back and draw on it and everything like that, and you can really get a sense and idea of these parts of the brain and their significance and how they contribute. But the nucleus accumbens, you can see right there, is near the base of the brain, and this is a part of the brain called the midbrain. There's also something called ventral tegmental area. That's what VTA stands for, and that is something that feeds directly into the nucleus accumbens, and that is also in the midbrain. That's often where this whole process starts with the reward pathway. So from there, so the midbrain is a very simple, is a survival-oriented part of the brain. It's just above the brain stem, and which has the most basic functions of all for life: keeping your heart beating, keeping the diaphragm moving so you can breathe, keeping your blood pressure up. And then the nucleus accumbens is just, the midbrain is just slightly above that, but it's involved with very basic survival mechanisms. It's the older part of the brain. So these signals don't start at the more complex, highly thinking part of the brain. So our ability to control that directly is really limited, because you're going to always put priority over basic survival skills, or your brain is going to do that, and it's going to override the prefrontal cortex when it's severe enough, when the midbrain is stimulated enough to initiate some kind of survival skill, it'll override the rest of the brain. So this is the beginning of the reward pathway. From there, the signals will go to the prefrontal cortex. This is just, I put this up here, I like the cartoon, but it also shows you we can actually stimulate parts of the brain. Hopefully it's not in a way that's as cavalier as on this slide, but actually neurosurgery is actually a lot of times safer to keep a patient awake. So the brain doesn't have any pain receptors, and you can stimulate parts of the brain. And if you're going to cut somewhere, you can stimulate that part of the brain and make sure that that's not involved in some kind of function like being able to see, or it's going to result in paralysis of your arm or your leg. And then you might be able to move a little bit to the right or left or forward or backward. So the nucleus accumbens, we've actually had a chance to stimulate this area in humans, in cases where neurosurgery was being done already in that area, and apparently the reaction is really quite remarkable. I was involved, got a chance to see a neuroscientist speak, who had done a lot of research in this area, and he had actually had access to some of these tapes. And so it was pretty remarkable, people's reaction when the nucleus accumbens is stimulated, and they'll describe it as this incredible euphoria, or an orgasm times 50 is what they report feeling. So we'll move to the prefrontal cortex. That's the part. That's the front part of the brain. So this is the next place in the reward pathway that all of the signals go to. After going through the nucleus accumbens, or an area that's feeding into it. And this is the more, so this is really the opposite of the midbrain. This is the more complex part of the brain, the one that is involved in those complex cognitive behaviors, executive functions, and so on. It's where moral code comes from, and it's also the part of the brain that tells us to stop doing something when we're thinking about doing something that might be dangerous or foolish. You'll get an impulse from the lower parts of the brain, the limbic system, the midbrain, and the prefrontal cortex is the part of the brain that filters that and says, okay, well, is that a good idea, or is this something that could lead to me getting fired, divorced, losing a car, getting injured, getting killed? And this slide right over here just shows, gives you a good idea of the prefrontal cortex. This is really the human part of the brain. This is what separates us from other animals. You can see in other animals it's much smaller. In the dog it's about 7%, in chimpanzee it's about 15% of the brain, and in humans it's about 30% of the brain. So even though we share about 98.5% of our DNA with chimpanzees, that 1.5% is focused in certain areas that make us very different, and the prefrontal cortex is one of the most, or arguably the most important area where that is stimulated by that that is stimulated to develop by that 1.5% of the DNA that separates us from other animals. And then from there it goes to the limbic system. So it goes from the nucleus accumbens or other areas associated with that to the prefrontal cortex to the limbic system. I'm going to go forward here for a second. So you can see the limbic system right over here. I like to describe it as, if you think of the brain as an avocado, the pit of the avocado would be about where the limbic system is and about the size of it. It contains, compared to the brain, it contains a lot of different structures, but I'm only going to focus on two because those are the ones that are really important to understanding addiction. One is the amygdala, and this is the emotional part of the brain, mostly associated with negative emotions, fear, anxiety, anger, things like that. It tends to be turned on when those emotions are high, and it tends to be suppressed when we're feeling good and we're feeling happy. And then the hippocampus is the part of the brain that converts short-term memory into long-term memory. So if anybody's ever, you can see that these two parts of the brain are very highly interconnected. They're right next to each other, and they are very, very tightly linked to each other. So when things have a very high amount of emotional content to them, we tend to remember those things really, really well. It really has a profound effect on the memory of our brain and some of the chemical and structural changes that are going to occur as a result of that. So let me see if there's anything. I think I pretty much said everything here. If you've ever seen movies like Memento or 50 First Dates, even though that's not an entirely accurate representation of what would happen when the hippocampus is damaged, it actually does give you a sense of that. Drew Barrymore's character wouldn't remember everything that day and then forget everything the next day. She would forget more as she went along. But people who have a significant damage to this part of the brain actually are stuck in time. If you have damage to this area at the age of 25 from a car accident or a stroke or something like that, at the age of 60 or 70, you may look in the mirror and not recognize who that person is. It's like you're stuck in time at the age that part of the brain is damaged, because you can't incorporate any new memories. You can remember things that happened before that damage, but you can't incorporate any new memories after that. Okay, so just again, I put this in to just reiterate the reward pathway. So again, going from the nucleus accumbens, ventral tegmental area, or an area associated with that, to the prefrontal cortex, and then to the limbic system. And there's another neurotransmitter, glutamate, which also is very important in memory as well. That's involved in that process between the prefrontal cortex and the limbic system. So when the limbic system is stimulated, it's telling your brain this is really important. Remember this. And why is that? Why is that? If we want to look at an example of that, we can just look at this right over here. So if I were to ask anybody, what are your memories of this day? Do you have very vivid memories? Do you remember things like they just happened yesterday? And people first noticed this, or a lot of people, it got noticed on a wide scale anyway. After President John F. Kennedy was shot, people noticed that, researchers noticed that people would have very powerful memories associated with that, and would be able to remember things like it happened the day before, or that morning, months later, years later, and even decades later. And that's going to happen with negative emotions. It's going to happen with positive emotions as well. You can think back to certain events in your life that have taken place, and you'll notice that there are very strong memories, and even things smelled and how things felt. So why is the brain set up this way? Because if we look at it in the context of our world today, that's not necessarily something that's going to help us out. In fact, it may be harmful to us. It could cause, it might be associated with PTSD. Why is it more important for us to remember what happened on 9/11 than something that we're studying for on a test to get our master's degree? Or why is that more important than remembering to pay the electric bill? Why do we remember that? Well, why is it that we have a hard time, even though we try to remember those things sometimes, but these other things just happen automatically? So let me go. So it's hard to understand in this environment that we're in right now, because we've created this artificial environment around us. We have to remember that civilization has only been around for about 7,000 years. That was only a small percentage of humanity around the Fertile Crescent. And throughout, let's just say, we're primates that we call humans, or consider people, going back more than 1 million years. So this time frame of 7,000 years or 2,000 years is really, really small in comparison to the total evolutionary time of development for brains. And then you continue to, the brain was developing because when you got a more complex species, it didn't just start over again and wipe the slate clean. It would tend to build on the survival mechanisms that had already been built into it. So if we go back to the environment where our brains have been developing the majority, the overwhelming majority of time, then we can understand that better. Okay. Let's see here. Something popped up on the screen here. So why is this important to our understanding of addiction? we can look at so if we go back about 10,000 years, 20,000 years, we can look at examples of this. For instance, if you were stumbled upon a wild animal, a tiger or a lion or something like that, and you were lucky enough to survive that experience, the more you remembered from it, the better your survival skills would be. Those would be our ancestors that tended to survive and then pass their genes on to the next generation, and so on. So those things, that were associated with those very strong negative emotions or fear, or things like fear, our brains would be automatically stimulated to remember that, because that gave us a survival advantage. Similarly, if we look at, so that's what this slide illustrates here. Similarly, if we look at something that's positive, going back again, say 10,000 years or more, you can kill a wild animal like a buffalo. The more you would remember from this experience, the better a hunter you would become. Those who were better hunters would be the ones that tended to survive more, pass their genes on to the next generation, and so on. That became more entrenched in our DNA as a result of that. So this is where dopamine would be released in these examples. And dopamine is not only released when you're getting the reward; it's also in anticipation of the reward as well. So it wouldn't be just when you're eating the buffalo; it would be involved in the hunt, in the kill, in the preparation of the food, everything. And things that we tend to be drawn to things that we think of as being bad for us. But if we again go back, say 10,000 years, we can see really why our brains crave things like sugar or fatty red meat. Because fatty red meat, for instance, was something that sustained us for a longer period of time when we didn't have a surplus of food and we were hunter-gatherers. And the more red and fatty it was, the more dopamine would be released, because that would carry us through for a longer period of time than, say, a chicken or something like that. Same thing with sugar. If you look at that, we tend to be, we tend to crave sugar more than other foods that we think of as being good for us. But anything that was really sweet would be a very rapid source of energy for our brains. And so again, our brains would tend to crave that, because that would give us a survival advantage when the sugar wasn't processed and when we didn't have it in excess. So that would be another thing that would help us to survive better. And so our brains got formatted by the dopamine. The dopamine was a way of prioritizing and telling us what was more important to our survival. And it tells our brain that every time we receive dopamine, and dopamine is released in the reward pathway. So we look at things that are released by dopamine, like food, water, sleep, sex. Food, especially when you're hungry; water, especially when you're thirsty; sleep, especially when you're tired; sex, of course, for the the species. All of those things are you release dopamine when you get them. So the interesting thing about drugs and alcohol is, here we also have dopamine released, but you get a release of dopamine that is 8 to 10 times greater than anything that you can get in the natural environment. And then when you put on top of that, we can manipulate it much more easily. We can increase the dose, increase the frequency. We can administer it in ways to get it to our brains faster so that we get more of a rush. And you can't do that with other things. Here's just some examples, and also all of these drugs really were derived from things that we found in the natural environment, or still grow out in the natural environment. Some examples, historical examples, for instance, in the 1960s, early 70s, the THC concentration was about 0.2%. Now it tends to be 8, 9, 10, 11%, so 40 or 50 times stronger because we've modified it, we've genetically engineered it. The same thing with alcohol, which we can actually find in the natural environment. We've observed deer and animals like that intoxicated because all you need is a source of sugar, which you can get from fruit, heat, which you get from the sun, and yeast, which you get from the air, and you produce alcohol. But they can only get up to about 11 or 12%. So we developed things like the still, where we can collect the gas from that, which boils at a lower point than water, and then and then recondense that, add that to the alcohol, making it much stronger. Another interesting example of this, I think, is the late 1800s, the Bayer company in Germany, and actually Bayer himself, who had developed aspirin from salicylic acid, which goes back to the ancient times of Greece 2,000 years ago. He added 2 acetyl groups to that, and that took away a lot of the nasty side effects. So he thought, okay, well, if I do the same thing to morphine, maybe I can come up with a cure for morphine and codeine. And in a way that worked. So he created, by adding 2 cell groups to morphine, diacetylmorphine, which is heroin. And patients would tend to prefer the heroin because it gets through the blood-brain barrier more quickly. And so you get more of that rush, and it's more addictive. This is just something showing different routes of administration. So we can see actually inhalation, the time to feel the effect is actually faster even than intravenous. And we've, so it's not surprising that we've come up with things like crack cocaine or crystal methamphetamine that you can smoke, because that gets to the, that affects us more quickly and gives more of a rush. And this is just showing some examples of how this occurs. In the lower right-hand corner, you see the cells that are green right there are the cells that are lining the blood vessels, and in the brain they're very tight. They're very tight. There's very little space between the cells, and that's to keep certain substances out of the tissues of the brain. But when Bayer diacetylated morphine to get heroin, it gave it properties that was more lipophilic or like the cells, so it could get through the blood-brain barrier faster. And this just shows you, it gives you an idea with inhalation why that is something that gives an effect so quickly as well. That as you go towards the end of the bronchial tubes and get to the very end, you have these microscopic structures called alveoli, which you can see in the circle on the upper right-hand corner of the picture on the left-hand side. And then you can see each one of those little grape-like structures would be lined by capillaries. So oxygen in this case is going right through, but if you smoke nicotine or heroin or something like that, then it would also go in very quickly. The surface area is tremendous, and that gives you an idea of why the effect occurs so quickly. So we've done all these things to manipulate the drugs to make them more addictive. So what this means is that these other things in the natural environment cannot compete. And it's telling the brain every time, not that you want the drug anymore, but I need this drug. I need it in order to survive. And not only that, but because we can get more dopamine from, especially from these newer drugs, then it overwhelms everything else. If you're getting much more dopamine from the drugs, every time you're taking the drug, you're releasing dopamine. It's telling the brain, and it's actually changing the brain chemically and structurally to crave that substance more, and it becomes something, the brain interprets it as something that is essential for survival, and not only essential for survival, but the most important thing for survival, because you're getting way more dopamine from that than anything else. So when let me go back for one slide just for a minute. So when we look at a rat that's pressing a lever, that's staying on a electrified grate and is actually burning to death, and it prefers, the survival part of the brain is telling it that this is more important than you being burned to death, getting the substance into your brain. And I talked about stimulation of the parts of the reward pathway, and that then later people did this with drugs and found the same results, at least in animals that had some predisposition towards addiction. So what this means is that drugs, alcohol, it's going to start off at the bottom of the list before a person starts using, or maybe after the first time, but it can very quickly make its way up to the top of the list and and the brain is changed to interpret this as being more important for survival than food, water, sex, sleep, being with your family, your job, any of those. So that explains a lot of what we do. This is another picture of a rat with that device where it can press a lever right over here, and that's pretty much describing what the survival mechanism and why it continues to press the lever even though it's going to starve to death or burn to death. And you can do the same things, by the way, in a dog or a monkey, and you get the same results. So another thing that's important to understand is the prefrontal cortex, the next part of the brain, the reward pathway that these signals go to after the nucleus accumbens, ventral tegmental area. It starts to be eliminated really from the pathway, and we know this because if we look at things like SPECT scans and functional MRIs, and PET scans that actually show us not only the anatomy of the brain but what parts of the brain are most active at any given time, then we'll see that that part of the brain will start to go dark. You know, we'll see it light up in certain blues and greens and things like that, but at first, in the early part of addiction, you'll see the nucleus accumbens, ventral tegmental area light up, then the prefrontal cortex and parts of the limbic system. But later on, you'll see the nucleus accumbens, ventral tegmental area lighting up, and parts of the limbic system. But the prefrontal cortex has just been eliminated. You know, it goes very dark, and you see very little activity there. So remember that this is the part of the brain that keeps us from doing things that may end up in divorce or losing our job or injury or death. That part, screening part of the brain, actually gets removed from that whole reward pathway. And this is just a slide showing, you see on the right-hand side the dark spot over there. It looks like a hole. That's not an actual hole in the brain, but that indicates the reduced level of activity that you have at that certain dopamine receptor that is in the prefrontal cortex in a person who has been in their addiction for a while. Now, all drugs, we found a common link between every single drug of addiction. All of them end up releasing dopamine in these high amounts, no matter what the drug is. And if you look at this next slide, I won't go through all of these, but you can go back if you want to and take a look at this. But it just shows you how you can go through every single drug and you can see how, even though there's other neurotransmitters involved so that they will feel different, dopamine is involved in the release every single time. The mechanism is different in one drug or the other, but you always end up getting that as part of the experience of having any addictive drug in the body. So this helps to explain why if a person gets addicted to one drug, they tend to get addicted to all the drugs. And really another way to look at this is that really the brain doesn't get addicted to the drug. It gets addicted to the dopamine that it's receiving. So it will, if you switch over to a different drug, then you're still getting dopamine, and the brain is craving more of that dopamine. You know, so you tend to have a problem if you're addicted to cocaine. Opiates, alcohol, other addictive drugs can still get you in a lot of trouble, even though that's something that's maybe not used at all or used very frequently, and a person tries to switch over to that drug. And withdrawal symptoms, those tend to reinforce the addiction. But another really critical thing to know about dopamine is that this is the only neurotransmitter that's involved that if we sever the pathway, in other words, we can use a scalpel or a cauterization or a small amount of acid, they've done this in animals, to destroy the nerve endings that are releasing dopamine or receiving dopamine so that it can't go through the reward pathway and exert its effects. That if you do that with dopamine, the animal doesn't want the drug anymore, even if it's going through severe withdrawal symptoms. You won't get that with any of the other neurotransmitters. If you do that with GABA, if you do that with noradrenaline, with the stimulants, the animal is still going to want the drug. It's still going to continue to press the lever to get the drug. But dopamine is the one neurotransmitter that we find if you cut off the supply to that, the animal doesn't want it anymore. It is the rate-limiting step, so to speak, in addiction. Other things modify that, but that is the one that is ultimately what causes us to get addicted to every single drug that's out there. remember that physical dependence is not synonymous with addiction. Don't fall in the trap of believing that or thinking that. So even blood pressure medications like clonidine or your beta blockers will give you withdrawal symptoms, but they have absolutely no addictive potential whatsoever. So what is important in addiction, and people used to make, and sometimes still do, make distinctions between physically addictive and psychologically addictive, and we need to just throw that out altogether because it has nothing to do with that. Psychological addiction is misleading. Just because something has fewer withdrawal symptoms or not as dangerous does not mean that it is just as addictive or more addictive than other drugs. It's that process of the dopamine release stimulating the reward pathway that is important in addiction, and which causes people to get addicted. Okay, so just another reminder of the reward pathway there. Now I came up with this analogy. This came from working with clients and maybe 2 months or 3 months into their treatment, even though they were talking sobriety, it would sort of come out that, okay, well, I was just talking about my drug of choice. They come to this conclusion which appears on the surface to be logical, and you find this in a lot of clients that, their drug of choice, let's say it's methamphetamine, but they'll have a drink every once in a while, they'll smoke a joint every once in a while, something like that, and they'll say, well, I'm going to stop my drug of choice, but those other drugs, alcohol, marijuana, I don't have a problem with those. I was able to take a little bit of that and stop. So I don't see, so once I get out of here, I'm going to go ahead and I'm going to still continue to use those things. And a lot of people end up in trouble and end up relapsing because of that. The reason why this is false, and this is why I came up with this analogy, you can think, let's say you have this guy, we'll call him Fred, and he is under house arrest, and he has 10,000 Hershey's chocolate bars in one closet and 10,000 Reese's Pieces in another. But then one day the police come and they say, okay, we're going to, and he gorges on the chocolate bars, but he can have just a few of the Reese's Pieces and then leave those alone. But if the police come along and they remove all the chocolate bars, he's left just with the Reese's Pieces, what is he going to tend to do? Now he's going to tend to gorge on the Reese's Pieces because he's craving sugar. And sugar is a lot more relatable to most people than dopamine. We all know the effect that sugar has on our bodies. We're not as directly familiar with dopamine, but it's the same idea and the same concept. It's if you're getting plenty, so in this example, if Fred is getting plenty of sugar from one source, he can get it from another source in moderation and be fine with that. But once you take that away and then you go to the candy that's not your candy of choice, and you've taken the other stuff away, then you're going to tend to, you're still craving sugar and you're going to tend to gorge on that. So it's the same way with dopamine. If you're getting plenty of dopamine from one source, it's easy to get dopamine in moderation from another source. And it can be very misleading to patients, and they can think, okay, well, I don't really have a problem with that. I've always been able to do that in moderation, and that is one of the things that really takes people out of recovery at a very high rate. That's one of the major problems with that. And just checking with the amount of time that I have left. So there's this concept of homeostasis, keeping the body in balance. This is something that's also important for survival. We can look at, for instance, keeping your temperature at around 98.6 degrees, keeping your body at a set point, which again is not necessarily advantageous to us now, but if we go back 10,000 years and we think, okay, during a time when we didn't have this excess of food and we're hunter-gatherers and we would go long periods of time without any food, then those of us who were able to, or those of our ancestors who were able to maintain their body weight were the ones that survived. So right over here, you can see an example of what happens here with, as a result of that. If you're flooding that space between the nerves with dopamine all the time, the body and the brain recognizes that as an abnormal process. And it'll adjust for that. So how does it adjust for that? It starts reducing the receptors on the neuron that is receiving all the signals. And for example, with a dopamine, you're flooding that space all the time, so the dopamine receptors will be reduced over time. What this does is this blunts the effect to anything that gives us joy in our lives where dopamine is involved. And it causes people to fall into a deeper and deeper hole, and the only thing that is giving them enough dopamine to where they really feel it is the drug. And here's another example of that here. This is another way to explain the same concept. There's this thing called the hedonic set point. And because of those receptors being reduced over time, that hedonic set point gets higher and higher. I use an example of a roller coaster here, but this could also be hanging out with your family and friends. It could be rock climbing or sailing or whatever activities that you really like. As that hedonic set point gets higher and higher, everything is falling way below that line. So as a result of that, the person tends to get more depressed in a bigger hole, and it tends to reinforce the addiction. Now we can turn that to our advantage in recovery. So after a while, it's nearly impossible to feel any pleasure from anything else. And in fact, the drug may just help you to feel normal after a while, not even give that euphoria that people are looking for. And you can also get that with other things. So patients end up in a worse position. If they're self-medicating for anxiety, those receptors for GABA, for instance, are going to be reduced. So it's going to be harder and harder to actually get relief from anxiety. You're going to get that temporary relief from the drug. But then after that, you always end up paying for that later. That good effect that you're looking for, like the anxiety-reducing effect, that tends to lessen over time. And the rebound, where you actually feel anxious and more nervous, will actually tend to get greater. And so anxiety actually gets worse. Depression actually gets worse. Maybe it works in the beginning, but people end up with worse depression, worse anxiety. And that's something that's important to explain to clients too. It's actually not, none of this stuff is helping them. It's actually making everything worse. Just a word on this guy, Gerald McLaren. He was doing studies in the 1960s, and he actually found by accident a strain of mice that loved alcohol, which was very unusual. And they will drink concentrations as high as 70%. Most mice hate alcohol. They won't touch anything with a concentration above 2% alcohol. They'll spit it out. They don't like it. But there was this strain of genetic mice that would drink and get really drunk. So what he did was he divided the mice that were not predisposed into three categories. You had mice that were injected repeatedly with alcohol, another group of mice that he put in a small tube for certain periods of time during the day to stress them, and a third group where he would nutritionally deprive them, especially of precursors that gave them that provided dopamine to the brain. So what happened when he did this was that all three groups of mice that were originally that didn't like the alcohol started to act more like the genetic strain of mice that liked the alcohol in the first place. And when he took away the stressors, they continued to do this. He later actually did autopsies on these animals, and he actually found structural and chemical changes that were similar to the mice that genetically liked the alcohol in the first place. So there were actually chemical and structural changes as a result of that. So substance dependence seems to be caused by a combination of genetic factors, environmental factors, and cellular changes from the exposure to the substance itself. And this just shows some studies. So I won't go through all of these, but this just gives you an idea of how some of the genes out there, how they work. We've looked at twin studies, identical twins. They tend, if one ends up being an addict or an alcoholic, there's a much higher chance, regardless of the environment that another identical twin is. If they're raised separately, regardless of the environment that they're raised in, they'll also have a higher chance of being addicted. And you see that in identical twins at a higher rate than you see non-identical twins and so on. And we can actually breed animals to be alcoholics and addicts in about 14 to 15 generations, or we can breed those traits out of them as well. This is just another example here. This is how antabuse disulfiram works by blocking the breakdown of alcohol, ethanol, to acetaldehyde to acetic acid. Acetaldehyde is very toxic, makes people really ill and sick. Acetate is much easier to eliminate from the body, and so that's why it blocks the step between acetaldehyde and acetate, so acetaldehyde builds up. In people of Chinese and Japanese descent and other Asians, I actually observed this in one of my friends, when I was in college, decided to partake in a night of drinking and watched his face turn bright red, the sweating, the flushing that was going on. So we actually see a lower incidence of people, Chinese and Japanese descent, and other Asian enzyme for acetaldehyde dehydrogenase, and they get sort of this natural effect, the same thing that you would get with antabuse or disulfiram, where the acetaldehyde builds up and has all those toxic effects that you feel from a hangover and so on. And then D2 receptors as well, we'll see that there are oftentimes fewer dopamine receptors in animals and in humans now that have a predisposition to addiction. So what do you do about that? Well, you look for ways to release that dopamine naturally in the body. There you go. So we have ways of compensating for that, but we can't just figure out by logic. We've learned ways to do that as time's gone on. And there's more than 100 different genes. They have different levels of penetrance. So it's not something where there's just like one or two genes that we can change, and I don't think there's any drugs that we're going to come up with in our lifetimes that's going to just make an addict or an alcoholic not one anymore. These other coping mechanisms and skills that we teach clients and that they learn in 12 steps are going to continue to be important for a long time, I think. And so the brain changes. We know that it's associated addiction and alcoholism with things like PTSD and depression, bipolar disorder, anxiety disorder, ADHD, and so on as well. And then here, this is the picture at the bottom is from Uppers, Downers, All-Arounders, if any of you are familiar with that book. And you can see the receptors over at the bottom of that. They'll get actually pulled behind the membrane as the addiction progresses in order to maintain homeostasis. But you notice that those receptors don't go away. They're just pulled back behind the membrane. So when that drug is removed from a person's system, all of a sudden now the brain's got to reach a new state of homeostasis. So it starts so now it's not getting enough dopamine. It's got this deficit of dopamine, so it starts moving these receptors back to the surface. And that's an important part of recovery. This takes time. It can take up to 2 to 3 years to get all those receptors back. In the meantime, though, that doesn't mean that a client's got to be miserable for 2 or 3 years. We look for other ways to make up for that dopamine and getting that dopamine through things like support groups and finding activities that people love and enjoy and dealing with those things in other ways through therapy and that kind of thing to compensate for that dopamine that they weren't even getting in the first place. And that's not going to tend to have this effect of just going down over time. The effect that you're looking for depression or anxiety actually tends to be maintained or even increased, like in meditation, it's the increase. And so you find something for treating those things that are actually much, much more effective than alcohol or drugs, which are in the end going to make whatever people are self-medicating for worse. So it's going to take some amount of time to heal. Clients need to know to stick with it. Salience, that refers to all these things that end up getting associated with sounds, visual stimuli, things like that, so that those so that stimuli will actually be associated in the brain, will be linked to those addictive substances. That can also reinforce the addiction, but we can also use that to our advantage as well. Once we take those away, those have less and less of a powerful effect, and the cravings start to diminish, and the other things that stimulate our brains to crave the drugs start to diminish. So that's all involved in treatment. This just shows this guy Childress who did an experiment where he showed people pictures of paraphernalia for 1/30th of a second. It was too brief for them to even know that they saw it. They wouldn't know that they actually saw the picture, but they would have changes in their brain that were similar to if you showed that picture for 5 seconds and they had time to take that in. So the brain is actually changing. It's actually releasing dopamine to these triggers even before a person is consciously aware of it. So what we do about that, Pavlov, just on him, remember he was a Russian scientist doing research at the turn of the century, and he was doing digestive studies, not looking at addiction at all. He was looking at the digestive system of dogs. So he already had a tube in their mouth to measure the amount of saliva that they were putting out. And he noticed every time that the tech walked into the room that the dog would start producing more saliva. So he designed an experiment where he would ring a bell every time right before giving the dog food, and then that produced a physiological response where if he just rang the bell even without giving the dog food, that it would start to salivate more. So later, people looked at, okay, well, can we extinguish that response? And they found that, okay, well, if you if you ring that bell and you don't give the dog food, the salivation gets reduced over time, or if you give it a bone, it has a different reaction over time, and that the salivation response diminishes. So we've done this now. This is really the basis for behavioral therapy, and so we associate triggers, like say an argument with a spouse or something like that, rather than getting angry and throwing things. We teach them to, okay, this is, you take a time out, you meditate, you play your guitar, things like that, and over time the brain starts to respond to those things differently. So we've got, I guess, just a couple more minutes here. So you can see, so when we look at 12-step programs, people say, well, we don't know how those work, we just know how they work. We can actually look at this stuff and see why that would be, those things would be effective. The trigger and the drug and alcohol are similar to the bell and salivation in the dog. Those triggers, every time you go to get triggered, you go to the alcohol or the drug. Pretty soon those triggers, you automatically start releasing dopamine, stress hormones, things like that, and the cravings get worse as a result of that. In treatment, what we do, and in 12-step programs, take 12-step programs as an example. If a person gets triggered, what do we tell them to do? Call your sponsor, call a sober friend, go to a meeting, talk about it in the meeting. We associate those triggers with different things, and with time, you're actually going to get a physiological response that is altered because you're not going to be releasing those chemicals that are causing that trigger, trigger to have its effect, and recovery gets easier, the cravings diminish. So this is really going through what I described about that. So that's how 12-step groups can actually work. That's an understanding from a neurobiological standpoint of how those things actually work, and a lot of the things that are done in treatment as well. Let's see. The placebo effect, this is something that's really important, I think, for clients to understand. This is good information for them, too. People have done studies where they have looked, they've actually set up like a makeshift bar and advertised a party and given people drinks. But they're virgin drinks. They don't have any alcohol. They simulate the taste of alcohol, and they've actually watched people change their behavior, loosen up. Guys will start to get the liquid courage and ask girls to dance and things like that, even when there's actually nothing, when they think something's in their system, but it's not. And if you look, if you think about the way that we've been socialized from a very early age, whenever you see people having fun, they've got a drink in one hand and a cigarette in the other or something like that. And so a lot of it is the socialization and the psychological effect, not the drug itself. So when we bring people into treatment and we're saying, okay, well, you can't do any of these things ever again, it can be very depressing for the client to, at first looking at that. Well, okay, you're going to be doing so. You're saying I can be sober, but I have to take all the fun out of life. A lot of the fun that we're having is something that we have some control over, because it's that psychological effect. We don't realize, that how powerful that psychological effect, not just that chemical effect, affects us, and we can get more of an idea, especially engaging people in activities that are fun. They can get a better idea of how those things can actually be enjoyable, and they don't need substances in order to to really enjoy those experiences. And I've had a lot of anecdotal examples of my clients doing the same thing with drinks or something like that, or somebody took weed but it was really oregano or something like that, and watched their behavior change. So it's not anywhere as devastating as maybe people tend to think of it at the beginning. And also, it's important to know that treatment, we see experimentally an effect at about 3 months, statistically, where we see an improvement in a person's ability to remain sober long term, to stay off drugs and alcohol long term. This doesn't necessarily relate. It doesn't necessarily have to be inpatient. At this point, there's no distinction. At this point, there's no distinction made in those, and so we want to try to get some kind of treatment, inpatient, outpatient, combination of those. Outpatient, we want to try to maintain that for at least 3 months if we can. So that's come to the end of this. So the bad news is addiction is a disease involving genetic and environmental factors. I call it a disease, but I don't think that's really important. You don't really need to make that distinction, in my opinion. But it's important for people to know that these, that there's actual structural and chemical changes that take place in the brain and how real this effect is. And the good news is that although addiction is not curable, it is a treatable disease with these things that you're replacing the drug with these other things, and clients can get sober and they can live a good life. Last thing, I sort of left this out. Remember that pathway that's established as a result of the trigger dopamine being released. If we start associating those triggers with other things, that pathway the effect tends to diminish over time, but it never goes away completely. So if we look at a dog, if we look at the Pavlov's dog, and then we recondition a different response with by giving it a bone instead of food or something like that, then that response of salivation decreases over time. But even after many years, if we start ringing the bell and giving the dog food again, that response of salivation comes back very quickly. So that's why people, even after long periods of time, will get into trouble as a result of that. That pathway is still there. It's just sort of waiting to be awakened. If we keep it, it's like a sleeping bear in hibernation. If we keep it asleep, then we're in good shape. But once we wake it up, we're in trouble again, and that can be many years or even decades later. And here, it's showing you some of the acknowledgments I have, try to give you a positive view on this. Turn the chart the other way, and I will turn it back over to. Turn it the panel back over to you guys.
Thank you, Dr. Arnot. We have some questions in the audience. First question comes from Randall. Using cocaine as an example, can you explain the role of saliency, drug liking versus drug wanting?
Drug liking versus drug wanting. I'm not sure what you mean by the distinction between liking or wanting, but you can make a distinction between wanting and needing with that. Cocaine or any other drug, it tends to be associated with the things that are around us, sounds, the lighting, whatever is going on, it tends to be linked and tends to get associated with that. So if you tend to use always in a certain area, or you get cocaine from a dealer that lives in a certain alley, every time you go to that area or every time you pass that alley, in the beginning, you're going to tend to get the craving because that becomes linked, and those two things become linked in the brain. Those locations, or it could be something like a stressor, getting bad news or an argument with a spouse or something like that. Those things become linked because our brains immediately start releasing those chemicals like dopamine because it has now linked those things, like the dog with the bell and the food. The brain has now linked those things together. So you get this automatic response. In recovery, you start to reduce that linkage because of the survival, because this is all involved in the reward pathway. coming from the lower survival parts of the brain, and the reward pathway is, our brains are formatted to that if the reward pathway is strongly stimulated, that's something very, very important to survival. So your brain starts interpreting cocaine or any other drug of addiction. If you have that predisposition to addiction, or once you get addicted to one drug, then you tend to get addicted to the others. So it's telling your brain this is important for survival. So you start to lose your ability to have, willpower. And we look at these other things that we're doing for treatment. It's not willpower, that we're addressing, because we found that that really doesn't work. But there are other ways of addressing that those problems that do work. And with time, then the brain doesn't link that with survival anymore. Once you get that out of your system, once you get alternative ways of getting dopamine into your system, then it starts to get to a point where your brain isn't saying, I need this to survive anymore. However, if you put that drug in your body again later on, then you trigger that reward pathway, and you can go right back to needing for survival rather than wanting. So I hope that answers the question.
Thank you. We have another question from Dr. Brewerton, and his question is, do you believe that so-called sexual addiction processes as substance abuse and alcoholism develops?
Yeah, people are looking more and more at those things, and they're looking more at food addictions and things like that. We're finding certainly there are similarities. Again, dopamine is released with those things. It doesn't tend to be released in as high an amount necessarily, but there are some things, so I think there's some distinctions to be made, and we're still really early in our study of things like gambling addiction and sex addiction and addiction to video games and things like that. We haven't done as much work on that as we have done on the effects of the brain from drugs. So our understanding is still in process on that. We're still trying to improve our understanding. There's a lot of things that we still don't know about how tightly those things are linked and how close they are to each other. Gambling tends to be, at least from the study so far, the one that looks most at the brain, and as far as the chemicals that are released, tends to be the one that's actually most similar to drug addictions and alcohol addictions. But there are definitely similarities. Dopamine is definitely involved in that process, but it may not be the same amount, and how closely those are related in terms of the effect on the brain is still being studied. So we're still working on our understanding of how what that is, what that linkage is, and how strong and how closely it is related to drug and alcohol addiction as far as the processes that take place in the brain.
Okay, perfect. Thank you. We have another question from Terry. How does this drug exposure relate to pregnant mothers and dopamine in infants in utero?
I'm sorry, can you repeat that question?
Sure. How does this drug exposure relate to pregnant mothers and dopamine in infants in utero?
Okay, I'm not sure. If you're looking at the overall effects. Infants, for instance, since these things the drugs can get through the blood-brain barrier, that's why they're addictive. They also get through the placenta, and so anything that the mother is taking, the baby tends to get that in very similar amounts with drugs, because those pass very easily through the placental barrier into the tissues of a developing fetus, and so they can be born being addicted to heroin or being addicted to any drug that the patient is addicted to, or that the pregnant mother is addicted to. The baby tends to be addicted to as well. And then there's certain changes that also take place with that we see with alcohol and with smoking as well in the developmental process of the fetus. So we see certain physical changes that take place as well. You tend to see those the most in alcohol. Fetal alcohol syndrome, the physical effects are more pronounced in alcohol than in most other drugs. That seems to be the one that's most associated with these physical changes that actually take place. You see less with things like opiates and that kind of thing, but those babies are actually going to have to go through a detox process after they're born to get that out of their system. And it is possible to remember exposure to substances is one of the things that predisposes a person to addiction. So that could potentially, we still need to do more work and study on this, but that could potentially predispose that baby later on in life to addictive substances.
Thank you. So G. Thomas wants to know what drug is known to have the highest release of dopamine as far as street drugs.
Yeah, methamphetamines, those tend to be associated more. Those have the most direct release of dopamine. You'll see that on the slide. If you want to go back, if you want to take a look at that later on, where I listed all the different, where I listed a bunch of different drugs and how they release dopamine. Methamphetamine releases it directly. Most other drugs release it indirectly. So if you go to cocaine, it keeps it in that space between the nerve cells for a longer period of time. So instead of that, the dopamine being destroyed by certain chemicals and being taken up into the presynaptic nerve, the nerve that the signal came from in the first place, cocaine will inhibit those processes so that you have more dopamine in that space for a longer period of time, and it can exert its effects more. And methamphetamine is associated with a very high rate of addiction, but that doesn't necessarily mean, we don't know if that necessarily means that that makes it more addictive than, say, a drug that releases it in an indirect way. What we actually find is that nicotine actually has the highest rate of exposure and that person later on getting addicted to it. After that, it is heroin, which so nicotine is about 30%, heroin is about 23%. Methamphetamine is around 18-19% of the people that are exposed will actually progress to addiction to that substance. So we don't know if that necessarily means that that substance is more addictive. And if we look at different substances, for instance, alcohol, for instance, marijuana, that has the lowest rate of people being exposed to it and later getting addicted to it. That's about 9%. But for those 9%, it's not going to make a difference. And people actually get into really serious trouble. We see this in teenagers who become, their performance goes way down in school. They become ostracized as a result of being social pariahs and known as stoners. We actually see very significant consequences as a result. So for that 9%, it's still, the addiction is still severe. It's still a problem. Remember, too, that once you get addicted, maybe not with nicotine, because that's a little bit different. It releases smaller amounts of dopamine, but more frequently. But with other drugs that give us those big surges of dopamine, once we were addicted to one drug, even if that person wasn't originally in that 9% of marijuana, they get addicted to methamphetamine or heroin or something like that, then they're going to have a problem with all other drugs of addiction. So now they are in that 9%. So you've got to keep them away from substances like that too, because that's going to stimulate the reward pathway and dopamine, and as a result of that, a person can get into trouble very quickly and then end up relapsing as a result of that.
Okay, thank you. Unfortunately, we are out of time for more questions. There are several more questions. If you have them, you can actually send them to ceu@solvehealth.com, and we will forward them to the doctor. If you have any more additional questions. We are actually I'm also getting a lot of questions about the PowerPoint presentation. The PowerPoint presentation, the whole presentation in its entirety will be available to everybody in about 24 to 48 hours, and we'll send you an email and notify you when it's ready so you can access it whenever you'd like. We are going to just wrap up the questions for right now. Thank you, everybody, for joining us for our webinar today. We appreciate you coming and spending your time to learn more, and we will be emailing you the additional information in about 24 to 48 hours. And thank you so much. Have a great afternoon, everyone.